Yeah, so now the meeting is starting recording also, and I will start with the presentation. As I mentioned before, we'll talk about this structural engineering workflow. We have already a model here inside of Revit well prepared with some structural columns, some beams, some slabs and walls, and we use this this model now to generate structural analysis and design. So therefore I have already prepared also some views. As you can see here on the right hand side, I have a view which is the analytical view of my Revit model, where already some adjustments are done regarding the analytical model. Therefore, we have some possibilities inside of Revit platform technology. We have also possibilities to apply some loads with different load cases. This is all done in the analysis tab of the Revit himself. You can define also some support condition if you like and create your load cases. This is all platform technology. Afterwards, we have the possibility to use the structural link between Revit and Sofistik, and this is all done in the Sofistik tab. As you can see here, we have some capabilities to export, to do a material mapping, to do a cross-section mapping, which means Querschnittzuordnung, because I have the German interface, unfortunately. We have some possibility to do that. Let's talk about that first. So first of all, we have to talk about the material mapping. If you click once to one of this functionality, normally the system dialog appears. You should be also be familiar with that. I will open the system dialog now manually. This is the selection of your code, with which code you like to do the design. In my example, I will use the German code now, but I think this is not the point, because anyway, the calculation process behind the model is dependent on the code, and we don't talk about into detail about this calculation and analysis process. But for sure, you have to select your code first of all, and then you can start with the material mapping and what's the reason for the material mapping. Therefore, I like to show you some properties of materials. Let's talk about some structural column properties, and we have a type parameter for the material in this template, and we have a material which is called concrete C2530, and as you can see, we can define a Revit material. We have the possibility to define some graphical representation, some rendering representation, and also some physical aspects. So we have the possibility to define some Young's module, which is defined in this property. We can define the Poisson's ratio, the shear module. We can define some concrete compression, but we do not have all the possibilities of material properties we need for structural purposes. So therefore, we decided in the structural link to the Sofistik to create a so-called mapping. So we try to analyze all the structural properties and try to identify regarding the code, the selected code, which Sofistik materials could be. And if you open this material dialog, the material mapping, you see that on the left-hand side, in the second column of this table, you see that all the Revit material will be indicated, and in the third column, all the recognized Sofistik materials will be applied to some Revit materials. And if the material mapping is not good because of some missing definition inside of Revit or some wrong definition inside of Revit, or if you like to manipulate some material properties which are not available in Revit itself, you can easily modify the material properties on the Sofistik side. So this means we are working right now on the Sofistik database and influencing some material properties regarding some strength or some other properties we have a possibility to modify inside the Sofistik environment. Or you can easily create also a completely new Sofistik material. If the material mapping is completely wrong, you can also create a completely new Sofistik material and apply that material to a standard Revit material. So that's the first point. The second point is to talk about the cross-section mapping. It's quite the same as for the material mapping. In my eyes, a bit more trickier, and for this reason I like to change in a 3D physical view. And I like to talk about a downstanding beam. So let's maybe select this downstanding beam and let's create a 3D view of this beam. So you see, this is now a clip box of this downstanding beam. This downstanding beam is supported by some structural columns, with 3 structural columns in this case, and is placed directly in a slab. The shape of this downstanding beam is a rectangular shape, so it's a parametric family inside of Revit with a height of definition and a width of definition, and for sure we can parameterize that elements and modify them inside of Revit. But the question is, how do you like to calculate this cross-section inside an analytical environment? And normally structural engineers in that case like to use some T-beam as calculation for analysis instead of the rectangular shape. So therefore we have additional parameter, or you can use also some structural properties. As you can see here, I have additional structural properties. To activate these structural properties, which normally on per default are not available or are not visible, you can go to the Sofistik tab and use the interface command for activating structural properties. So you can switch on and off the structural properties of certain elements. And in these structural properties, we have a parameter which is called mitwirkende Breite, which means effective width. So that means you can use a certain width of your slab in addition to the rectangular T-beam to create a rectangular cross-section, to create a T-beam out of the slab and the rectangular shape of Revit. And you can influence the property of the Revit element with these Sofistik properties, or you can also do the cross-section mapping. And as you can see here now that we have a rectangular beam which is called 30 by 150 centimeters, which is a rectangular shape inside of, and we recognize that in the cross-section mapping, so quite the same as for the material mapping, as a T-beam. And you can either now use the parameter inside Revit directly to add additional information for this T-beam, or you can also simply use the rectangular shape and apply a new cross-section to that rectangular shape as you like. You can also manipulate now some values of this rectangular shape which are important for analysis, maybe some concrete cover for rebar elements and so on. So this is all possible to do now in this cross-section mapping dialog. So I will switch off again the 3D section box. So we have talked about material mapping, we have talked about cross-section mapping. So an additional point to that is the action mapping, because also this is important. We can define some actions which will be applied to the loads, because we need actions, because in Sofistik analysis we need the actions for the Eurocode concept of superpositioning. That means applying some safety factors, partial safety factors, combination factors. So therefore we need actions, and to recognize the actions you can add in the Revit environment with the Sofistik actions, you need also to maybe open again the action mapping. And also here we have some actions in the Revit database, which in this case are snow, which is Schnee, or self-weight, which is Eigengewicht, and we can apply a mapping with the Sofistik actions here directly. The same thing here, you can apply different actions or create a completely new actions. You should be also familiar here with this load case manager, where you can apply new actions quite easily, and you can apply that to your load case or to your action inside of Revit. So now we have well prepared the Revit database. We have defined all the mappings, material, cross-section, and actions. After applying the load, which is quite a Revit functionality, we can now go to export this system to the Sofistik platform. So we are still now in Revit, and now we will move to the Sofistik platform. So therefore, we have the possibility to use the export button. So in the export dialog, you see that we have 3 different possibilities to use the export button. The first possibility is to use the export of the entire Revit database. So I don't like to use this concept because normally in Revit we don't talk only about 3D, we talk about 4D. So that means we have also the time and the envelope regarding the time of this building. So means that maybe you have some temporary elements like temporary columns which are not available in the last stage of the building, and there are already in the Revit database, but we don't like to export that to analysis. Or we have some different design options where we like to export only one of them. So if you use export the entire system, you will export all the Revit elements saved in the database. So therefore, my preferred option is to use a so-called partial system. This is the second possibility inside this dialog. We can export only a partial system, and partial system means you can either select some elements, or if you have no selection active, we will use all the visible elements in the Revit view. So therefore, you can set up a view where you activate the last stage or the last phase of your Revit model. You can activate certain design options. You can also hide or do visible some elements you like to export or not, and you can prepare your view for exporting to the Revit, to the Sofistik database. And that's my preferred option, to maybe export also the entire model, because you can simply activate visible all on and then go for the export. Then we have some parameters for meshing, what's the mesh density and how the mesh is going from a fine mesh to a coarse mesh. You can export foundations or not if you like, and you have possibility to do some mesh refinements. So I simply now click to OK, because now the settings are already well done in this system. And you see now that we export the elements to the Sofistik database, we will do the meshing, and then you have the possibility to open the SSD, which is the Sofistik structural desktop. So now we are moving to the Sofistik environment, and we see here that we have now the Sofistik database. So we see an overview of the meshed system inside the Sofistik environment SSD. You see we have meshed all the elements. We have created also some intersection between some elements like columns and slabs and so on. So the meshing is very good here. We have the possibility to also represent some different groups, because we have the possibilities to assign also groups already in Revit, which is quite important for construction stage manager calculations, or maybe also for post-processing if you like to show results only for certain groups. And you see now a view where the groups are represented in different colors. So this is already possible inside of Revit. And afterwards, you see in the task manager, which is already Sofistik functionality inside the SSD, where the materials are applied, where the cross sections are defined. We have also a soil profile, which we don't talking about now. We have the possibility to do the calculation of linear analysis, and I will open that task. And you see that we have 4 load cases in that example. We have the self weight, we have variable load, we have some wind loads and some snow load. And we will now run the analysis for these 4 load cases in linear analysis calculation. And when you click on the system visualization, we can also visualize deflections or deformations of that building regarding these load cases. You see now the deformations regarding self-weight. I will activate the deformations regarding wind loads. You see a horizontal deformation. For sure, the deformation of wind load is quite different than for self-weight. And this is now done by Sofistik using the finite element methods to solve the equation system and to get the results for these single load cases. For sure, we have now the possibility to combine the load cases, to use the construction stage manager, and I have also prepared a construction stage manager where I simply use stage by stage construction, so floor by floor in that case. For sure, this needs a little bit time to calculate because it's there are more steps to calculate all that processes, and then you get results of all these single load cases. So you see that we have now the first construction stage regarding self-weight, the second construction stage, and so on, and you can activate for each construction stage your result visualization. Okay, I don't like to go into detail for that part because this is more structural analysis part, and if I'm informed correctly, you have also training regarding this part. So we will talk only about the workflow, so interface between Revit and the analysis, and I will give you a short impression for sure what you can do with these elements coming from Revit. Did you have any questions regarding that part? You can either use your chat for questions or you can activate your microphone. So I can't see any questions from Paul. That's quite good. I have some feedback, so I can be sure that you are already here. So that's good. So let's continue with the next concept. So you've seen that we have now exported the entire system, so it means it's a 3D model, and you can use this model for all the calculations you like to have, especially for construction load cases. You can do the wind analysis, you can do some dynamic analysis, you can calculate the load takedown of the loads on the foundation level, and so on. But structural engineers normally like to calculate some different systems in the building, and for that I will take an example, and one of the best examples in my eyes is a slab. So normally structural engineers like to analyze the slab not in a 3D system, but they like to calculate a certain 2D slab system to define the analysis and the design of the rebars, especially on this particular slab. So and therefore we have prepared different views. So I will switch now in the view of level 1. So this is floor 1, and you see that I have isolated certain elements. In that case, I have isolated all the slab elements, the downstanding beams, with the corresponding loads for sure. And I've done this for all the levels. You see for level 5 I have the same, for level 4, for level 3, and so on, for level 2. So you can now export all these single subsystems, so that's the name for these partial elements. Now we give you an explanation why this is not a partial system but a subsystem. And you can export slab by slab, and then also using some load takedown functionality I will show you afterwards in the SSD. But first of all, let's talk about some problems we maybe have calculating this slab. So first is that we have some variable load. So this is this highlighted load now on my screen. So this is a variable load on the entire slab, and normally structural engineers like to create some load patterning. So to divide some loads, to have loads on each single span, to get a minimum maximum envelope of bending moments and shear stresses and so on. So therefore we have in the structural interface of Sofistik, we have a tool called load patterning, or Flächenlastteilen in German, and you have the possibilities in that case to select the command. Then you can define on which load case you like to apply the divided loads. So I will start now with the load case 101 for the first divided load. You can select your load case for dividing, and the lines, which are simply model lines, you see the highlighted lines now are well prepared model lines from my side. The structural engineers can decide to create some model lines for the load division of your load patterning. And when you click on Finish in the option bar on the left top of the Revit UI, you see that now you create some divided loads. You can see here we have all the loads divided with some different load cases. In this case, the load case number 119 is applied for this single part. And this is already done for the floor number 1. So this is the first point, load division for load patterning in a 2D subsystem. The next point for subsystem, if I export only a slab with the downstanding beam, and if I do this as a partial system, I get a finite element mesh of that beams and of the slab, but I don't have any support conditions, because in this view there are no support conditions for sure, because the support conditions are defined in the foundation level of the 3D system, and I don't like to create additional supports in that view because this is additional work I don't like to do, and therefore we have this subsystem export concept. And subsystem export concept is a third possibility. As you can see in the export interface, this is the possibility to export an additional database. You can see you can indicate a new database name here in this additional line. So you can create additional databases from one Revit model, and this is one of the best concepts in my eyes. We have one single Revit model, and we can extract a lot of analytical databases to do the design, because structural engineers like to have different models for different calculation purposes. So, as we discussed before, for dynamic, for wind analysis, and maybe for construction stages, I like to do that on the 3D system. For slab design, I like to use a simply 2D system. Or maybe I can use also only the core, to export the core for the wind analysis. So I can decide as a structural engineer what I like to do with my Revit database in the analysis environment. So therefore, subsystem uses the visible elements, in this case slabs and beams, and then, and that's quite tricky stuff, we have the control parameters in the second tab. We can analyze all the connected elements of this slab in the database. So that means when we extract the slab and the beam, this subsystem concept checks the entire database and checks if there are some connected elements to the slab, which in this case are the downstanding columns and the walls. And these connected elements will be used for creating some support conditions. And you can use the support conditions for 4 different directions, or for 3 different directions, and for the rotation degree of freedom, to calculate support conditions or not. As you can see here in that part of the dialog, first of all, we define that we like to calculate on a 2D system and not on a 3D system, which is also available, because you can use any partial system to create a subsystem inside the analytical environment. We can define the axial stiffness, which is the first line in that part, of the connected elements, and let's discuss that on a column. So if you take a look at the column, a column has an axial direction, which in this case is the vertical direction. And you can now use this axial direction or neglect this axial direction. If you select keine, which means none, you have the possibility, you neglect all the vertical directions for support. So this does not make sense in this case, but as I mentioned before, we can use any 3D subsystem, especially also for the core. Maybe I don't like to support the core elements vertically in some elements, so therefore you have the possibility to neglect the axial stiffness. In that case of the slab, for sure you have to activate that, and you can define the axial stiffness of columns as a fixed support condition. So therefore means if you select this fixed option, or fest in German, you can apply a vertical support condition which does not allow any deflection at that point. And you create a 2D slab with vertical supports where on the support lines or points as walls or columns, you don't have any deflection. And also here, when we talk about slabs which are supported by single columns, normally you get some singularity on that point, and you get worst bending moments and have a lot of shear problems if you use some fixed support conditions. So therefore you have also the possibility to create an elastic spring node instead of the column, and you will calculate the elastic stiffness of that spring regarding or dependent on the downstanding element. So you have a column underneath your slab which are supporting the slab. This column has any information we need for the analysis of this spring element. We have the length of the column, we have the cross section of the column, we have the material properties like the Young's module. We have seen that in the material mapping. And with these three parameters we can calculate an elastic stiffness on which we can apply in addition a factor. So maybe you don't like to use the entire elastic stiffness of that column, so you can reduce that maybe by 10%, simply indicate here a 0.9 value to use a factor for this elastic stiffness. And you can do that for lateral stiffness, for shear stiffness, which is not available in a 2D system, but will be active in a 3D system for sure, because in a 2D system for sure we have deformations and we have forces only perpendicular to the plane. So therefore no lateral displacements, therefore also no lateral stiffness activation possible here. And last but not least, we can activate also the rotational stiffness. So that means on the certain connected points of and walls, we can release or we can completely fix the rotation elements of the slab. So also here you can use a fixed rotation or a released rotation, so you can define the rotation as free in the system, or you can use an elastic behavior. So simply also here we use not an axial stiffness of the column, but a deformation stiffness of the column to define a rotational stiffness. So if you are interested on the exact concept how they are calculated, you can for sure use the manuals of Sofistik. In the manuals is well described how these elastic springs will be calculated in the Revit interface. So when we export now this slab, now we create an additional database. So for sure also here some elements will be exported, we will mesh the element, and I have prepared that already for the entire levels. We have discussed now for the floor number 1, and if I open the floor number 1, you see that we have now exported this subsystems of only this 2D system with the downstanding beams. We have activated all the linear support as springs, as we have defined that in the interface. And you see some linear springs where walls are underneath the slab. We see some point springs where we have the columns, and you can for sure now also here run the analysis. Okay, but before we run the analysis, we have to discuss one point, and therefore I will switch again back to 3D physical view. What we have talked about now is this part of the building. So we have talked about the first floor. The first floor is defined as intermediate floor. You see we have some supports, but we miss some support of these rows of the column. And that's quite tricky, because as we don't have any support, for sure we have a load which is going on that slab. And if we take a look at this view, you see that there is no load coming from top which is influencing this slab on this view. So therefore, if you are running now the analysis of that slab, we don't have correct values because we are missing all these singular loads which are coming, let's go back to the 3D view, which are coming from the floors above. Because for sure we have here some load takedown which will going on that beam, and this beam will transfer the load to the additional columns in the first floor. So therefore, going back to the Sofistik environment, we have a task which is a simple text pad where we can copy some support conditions from the subsystems above. As you can see here, we have a lot of subsystems. We have the subsystem level 5, level 4, 3, 2, and so on. And this subsystems has already some data results. So we have some support results inside this database. And going back to the level 1 floor, we have a text task defined where we can create new databases, in this case type of G, which G means self-weight, and we can simply copy in new load cases from the database above, in this case for the floor 2 database, and we copy all the support forces as load in this new database. So therefore we get the entire load takedown directly in this 2D subsystem database, and when we calculate all that stuff, so we calculate also this text task, then we extracting all the loads from the subsystem above, we apply that on the database in addition to the loads coming from Revit for this subsystem, and when we define this deformation, or we're showing this deformation, you see that we have additional load cases like the load case number 10 and 20, where we definitely get only single loads, and I can show you that also in the post-processing tool called WinGraph, that we have the loads. Let's talk about input loads. You see that we have this area loads here coming from this is the self-weight, is not a good example. You see that we have all these pattern loads defining by the load patterning, and we have the self-value as single loads coming from the subsystems above. I will give you also a better impression of the values. As you see here, for example, in the middle of this T-beam, we have a load around about 1 meganewton, which is coming from the top systems for self-weight. We can activate that also for the variable load or for the snow load, and all these loads are applied now in the subsystem. And now with these loads and with these results, as you see also here, single results for each span, we can now combine that load cases by using Maxima as tool. So that means we can do a superpositioning regarding the rules for all that load cases, and at the end of the day we get combined results, and we get also results for doing the design, for crack design, for ULS, for SLS, and we can use all that elements for defining that design. Before we start to define the design, we need to define also the concrete cover. So that means we need to define where the rebars are placed in the slab to calculate the correct position, because this is definitely needed to do the analysis of the design for the rebar elements. And afterwards we can define the design, and as you can see here, these are all the load cases which are used for this design, and the maximum value gives for sure the correct rebar results. I will calculate now the ULS of this slab, and afterwards I will show you some results. As you can see, oh, this is I don't like to use this. Let's calculate also the SLS, so defining checking the steel stresses, checking the crack width, and if we need additional rebar regarding SLS, we insert new values in our database. And last but not least, for sure you get the results. As you can see here, these are pictures now from the Revit, from the Sofistik database. I see now here in that case the bottom rebar requirements of reinforcement in main and minor direction, and the same for sure of the top rebar calculation. You see this, the top rebar requirements for main and either for minor direction, in represented now as ISO lines or as ISO areas. In that case, for sure you have any possibility to define ISO lines or also some vector, tensor values in some nodes. So you can change your representation as you like. Afterwards, and I will run that now only to give you an impression, I can do the design also for some beam elements. So let's do the same as for slabs now here for beam, because we use afterwards these results inside the Revit database to creating rebar. So again, I will ask you if you have any question on that part. So what we have seen now is using the Revit model for analysis and design in different methods. So one method is in generally the 3D system export for the dynamic analysis and maybe wind analysis. And the other concept is this so-called subsystem concept, where we can export only parts of the building and generating automatically the support elements of this part. Are there any questions? No questions. Okay, good. So now let's move back to Revit and let's talk about all the rebar stuff. So I will close the Sofistik environment and I'm again back into Revit. So in the Revit model I have prepared a 3D view which has a certain transparent representation, because the problem, if we're talking about rebar, reinforcement are already inside some elements like columns or beams or slabs. And if I do a standard representation which is not transparent, for sure I can't see the rebar elements because they are hidden by the element itself. So therefore I have a special view here. It's called 3D rebar or Bewehrung in German. And now let's talk about this slab and this downstanding beam. Okay? So let's talk about first on the downstanding beam. I will select the downstanding beam. Then I move to the Sofistik Reinforcement tab. And the Sofistik Reinforcement tab has two modules integrated. One part is the Sofistik Reinforcement Detailing, which we need afterwards to do the rebar draftings. And the other part is the so-called Reinforcement Generation. These are two different pieces of software with two different prices for sure. And I will start now with Reinforcement Generation. Reinforcement Generation is a tool which takes a look to Revit results, imports the Revit results, sorry, not Revit results for sure, we talk about Sofistik results. So use the Sofistik results, import the Sofistik results in the Revit database, and then we will generate drawings, rebar elements out of that results. Okay, this works for standard beam element, for standard cross sections on columns, for slabs and walls if they are not slanted or have different variable thicknesses and so on. So if the geometry is quite tricky, for sure we can't use a standard generation tool, but anyway I will show you also how you can generate some additional rebars by using native commands in the Revit platform environment. So therefore I use the create function now. So create function means please create rebar regarding design results. And as you can see here, we can use results from Sofistik database, or we can use also different results if they are stored in Revit result packages, I think is the correct name. So you have sometimes, if you have some structure analysis links to different analysis tools, you can also insert result packages in the Revit database, and we can also use that result packages. In my case, I will use the Sofistik database, we see a list of all the Sofistik database. As we have mentioned before, we have the 3D building database for the entire building. We have used for wind design and construction stage manager. And we have all the subsystems. And as you remember, we have defined the analysis and the design for the level 1. Therefore, I select the level 1. We have load design cases, which is ULS and SLS in that case, are simply defined by numbers, because in the Sofistik database we define for each task a number of the design. And I will use now the highest number because this is the number where the maximum requirements are stored in the database. For the results, the beam element is already selected. For sure you have also the possibility with this Elemente auswählen, which means pick elements, to select elements afterwards. I've selected elements already before starting the command, so they are already active. Then we have possibility to define some base reinforcement. So in my case, I like to use 2 bars of 20 diameters in the bottom of the beam. Oh no, in the top of the beam, sorry. I can use 2 diameter of 20 in the bottom of the beam, and I can use some stirrups. In my case, let's define a stirrup diameter 10, each 300 millimeters. So this is the requirement of the minimum rebar I use, even if the design values are lower than these inserted values. And then we can talk about some settings. I will activate also now a visual representation of results, and we have some constraint files. So we can talk a little bit about this constraint file. You see that we have some possibility to define which bar diameter we like to activate. We can define if this is a beam, please use only bars smaller than 28 millimeters. And depending also on the section height, you can neglect some diameter. So if the section height of the beam is smaller than 40 centimeters, please do not use bars with a diameter of 25 and greater. You can create the same rule for columns and so on. We can define some rules for spacing of the longitudinal bars and so on. So I have many rules you can influence here for creating your rebar. So that means basically you have the possibility to use the design results, create your own rules to define the correct rebar elements which are filled the requirements of the design results, which you see when we're creating now the rebars, because we have a very good representation of results. So I simply click on OK, and now all the rebars will be created belong the design results. As you can see here, we have some representation. The blue area are the existing rebars now which are defined in that element. The red ones defines the requirements of that rebar, and if you see here, we cover of course the requirements by the rebars, or what's also quite nice to see, if we select some rebar elements here, let's select in this rebar element, and if we shorten the rebar, you see in real time that now the blue area is getting smaller, so you can completely see if you are filling your requirements or not. Okay, so it's quite a real-time response of your results and your inserted rebar. So if you delete for sure this rebar, you see immediately that you need additional reinforcement in that part of the beam. Okay, so I will go step backwards to refill my requirement, and if I stretch my rebar, now you see that I will fulfill my requirements with this part, with this generated rebar element. This rebar will be generated now completely automatically. You see all the additional rebars also in this top part for this negative bending moments. You see the additional bars in the bottom of this beam, which are shorter because we don't need it on the entire length of the beam. You see that we have the stirrup with the spacing of 300 and with some smaller spacing of 200 in the part of the column because of the shear requirement. So this is definitely generated automatically, and for sure you have the possibility also to define or to modify your elements by using different layout rules, using additional elements, defining different diameters and so on. So you can influence the rebars manually also afterwards. Okay, again, are there any questions on the generation tool of this beam element? No question from Paul? No question from Brit? And I suppose also no question from the other attendees. So I will simply continue with the presentation of the next steps. So let's move again this group in the ribbon back again. Now let's move generating some rebar elements. So in my example, I have already prepared some sheet. As you can see here, this is a sheet for this representation of the T-beam. So this is simply done by Revit, standard technology, creating some cross sections or longitudinal section, placing and layouting this cross sections on the sheet, maybe inserting also a 3D view of that system, having a title block with all the parameters of project number, sheet number, and so on. And what you see here is that we see all the rebars visible. And what's quite tricky now, that when we talk about reinforcement detailing, we have to talk about concepts. So what means reinforcement detailing? So normally when we talk about reinforcement detailing, we have to assign, first of all, marks to the rebars. So that means each bar which has the same geometry gets the same mark. And normally we do that sheet-wise. So that means we take a look at the sheet. If we have the same geometry of rebar on the sheet, we get the same number. If you have a different sheet, you can have additional in that sheet the same number of the bar with different geometry of the first sheet. So therefore we have to assign all the rebars to a certain sheet. And you can do that simply by either selecting all the bars and doing the assignment, or if you don't have any selection, all the visible elements will be applied to that sheet. So let's take a look first of all to that stirrup elements. And we have an additional parameter called soft sheet. And you see this soft sheet parameter is still empty. So that means all these rebars are not assigned yet to a sheet. Oh, Raul has left now. Hopefully is coming back in a few seconds. So that means I have the possibility to select these elements, and there is no assignment defined. So I will cancel now the selection, and I will use the assign tool. It's called Planzuweisung in German. In English this tool is called assign, and now I can assign to all visible rebar elements a certain sheet. As you can see here, I have a list of all the sheets defined in Revit, and I will use the sheet number TO2, which is the sheet of this T-beam, and I will assign now this T-beam, this sheet, to this rebar element. And as you can see here now in the soft sheet parameter, we have now the number and the name of the sheet for the assignment. We will use this assignment also for different other stuff, but I will talk about that later on. So that means now we have already done the assignment. Let's go back to the T-beam, and now we can start with the annotation tools. So therefore I will activate a certain view. I will activate the view of the longitudinal representation, and now I can tag all. So this alles means I will tag all the rebar elements in that view with certain rules. The rules are defined by the settings. So you can take a look at the settings. Don't discuss that on detail. You can select first of all which Revit family you like to use for annotating or for tagging. You can define which linear dimension styles you are using, if you use multiple rebar annotations or not, how many numbers of rebars you need to have certain annotations and so on. It's quite tricky stuff, but I think for the first step you should be able to use these standard settings, and when you use the Tag All tool or this Alles beschriften, then we check all the elements and we place some annotation elements depending on the rules. As you can see here, for the stirrups, we define a dimension line with an annotation tool. You see that we have a circle. In this circle, you don't have any information yet. In this circle, afterwards, we should see the bar mark, which in this case is still not existing. Therefore, this circle is empty. We have a number of bars, which are 24 pieces. We have a diameter of the bar, which is the diameter 10, and we have a spacing of the bar, in this case 30 centimeters. So this is the definition of that bar layout. The next one is this one here. You see also here we have stirrups, we have 30 pieces, diameter is 10, but the spacing is only 200 millimeters, and so on. We have representation of the bottom layer, which you see here, 2 bar diameters 20, 2 bar diameters 28 for additional rebar. You see also the indicator and the leader of these lines, and you have the same for the top rebar. 2 diameter 32, 2 diameter 32, and additional also 1 bar diameter 32. So what we are missing is the bar mark, and you can simply using the marking tool, which is called apply mark, or in German is positionieren, and if you are using this tool, you can define at which number you like to start with your bar marks. We start with the number 1, and what's the increment of the bar mark. So that means starting with 1, the next number is 2, 3, and so on. You can do that for rebars and also for fabric elements. And as we have discussed that we talk about sheet-wise concept, we have to do the bar marking for each sheet in a different way. And I will do that now for the sheet of the TB. You see now that the geometry will be now checked if we have same geometry, and you can see that on the stirrup. You see that the stirrup gets the bar mark number 1, and also this stirrup, because we have the same geometry, gets the bar mark number 1, as you can see here. Instead of the longitudinal bars, gets bar mark 2, bar mark 4, and 3, and so on. And also for the top bar, we get the same bar mark 2, because we have 2 diameter 20, which are along the entire beam. We have different other bars for this supplementary bar, and we have also a tool which is called bar end, or in German Stabende. You can place this element to defining a representation of your bar end, as you can see here. You see, oh, this is wrong, let's use this one here. You can see here that we have here a bar with the bar mark number 9, which is finished on that part. So you can place all these symbols for each bar end, left and right, to understand where the bars are finished, because it's quite tricky to see in some cases. And you see here that now you know that the bar 8 is finished here, and the bar number 7, for example, is ending here. So you have all the possibility to define your marks. Now let's miss also the bar number 9. You see that you can indicate, and also the 8 here is missing. You can indicate for each rebar element a bar end symbol in that case. Okay? So for sure, all these annotation tags are standard Revit elements, so you can move that, you can rotate that if you like, to place in a horizontal way. You can influence the linear representation if you like. So you have all the possibilities we have in Revit. So this sounds quite good. What we need, especially in German, I'm not sure if you need that also in your country, we need a so-called, in German is Stabstahlauszug. So this is quite a representation of the bended bar outside of the element. So we have the possibility with this bar extract or with this bending shape detail to define the bending shape of each bar and create a 2D representation of that bending shape. As you see here, we define now a symbolic representation of this bar. You see the bar mark is indicated. We need two pieces of bar diameter 28. The length of the bar is around about 7 meters and is indicated also for each segment length. I think that's quite interesting. If you take a look at the cross section, let's first of all do annotation of the cross section. You see that we get also here all the elements. You see the diameter 2, the bar mark 2, the bar mark 6, the bar mark 5, all indicated here in the Revit element. So this could be, we would use that as vertical, the representation of the stirrup here. And you can define also here a shape definition of your bar with all your indications of hook length, of segment length, and of the entire numbers of your bar. Okay, you can move that also on the right hand side. I think it's quite better to get also readable all these values. You see we get an indication of each segment length, and we have also an indication of the entire length and of the number of the bars inside this for this bar mark. Okay, I'm not sure if you need that in your country, but this is definitely needed in Germany here, and you can use that for all your bars also here in this view to place a representation of the bar number 9, to place a representation of the bar number 8, bar number 7, and so on, to see all the supplemental reinforcement here on your sheet again. Okay? So you see these are all the bars which we have placed now in this beam. Okay? You see the bar number 7. Funny here. Oh, I selected the wrong bar here. This should be the bar number 7, this one here, not the number 2. This was my mistake. You see, this is the bar 7, 8, and 9. So all the supplemental bar are here defined. And for sure, you have also the possibility now to manually add some, if you like, some dimensions to understand where to place your bars. You can dimension that also maybe from the grid line number B to have definitely a correct representation or position or location of your additional bar in that beam. So last but not least, maybe we need certain representation of stirrups, because in some countries they don't like to represent all the stirrups on this sheet. So therefore we have a possibility to hide some elements. So it's called Stede ausblenden in German, or hide rebars in the English version. You can select elements and you can apply a symbolic representation to that bars. So that means now we will hide the rebar elements and define only a representation of the first and the last 2 bars. You see here, only the first and last 2 bars are represented. You can for sure influence that values by parameters to define 3 bars at the end instead of 2. And you can do that for sure for the entire beam to simply get a different representation of your bars. And if you like, which is also done often, use or move your dimensions directly inside this beam, and then you can see definitely that the bar number 1 with the spacing of 200 starts here and ends here, and so on. So you have many possibilities to influence the representation on your sheet you see the additional information all on your sheet, and what we are missing now is the bending schedule, so you can apply a bending schedule automatically. Also here, this is the bending schedule only for that sheet, and this bending schedule is now also in German. You can also here switch easily that to English, or set up already an English schedule before opening the schedule, and you see all the bar marks from one with the number of the bars, with the diameter, with the length of the single bars, with indicated weight, depending on each diameter, and you get also the sum of the weight and the total weight of the bars. In that case, we need around about 1 ton of rebar in that beam, and for sure you get also a bending schedule for all the bars. You see here the stirrup, the bended bars with the shape code 31, and all the straight bars defined here with all the informations for the manufacturing and for the fabrication of the bars. And for sure you have the possibility to import that bending schedule directly on your sheet and place it wherever you like, to print out that sheet even with the including bending schedule. Good. So this was now the first part of the rebar. We will talk about later on also using a slab. Did you have any questions regarding rebar till now? I know that it's quite a lot of information for you, so hopefully you can understand all that information, but anyway, I record that meeting and I try to send it to you afterwards. So therefore, there is no question I see, so therefore let's continue with defining some rebar for some area elements, maybe like a slab. So let's switch again to a different view. 3D view of the entire building. We have talked about this beam now. Now let's talk about this slab. So as you remember, we have also done the design for that slab already. And we can use also here the design values to generate rebar from this database, using some rules, using some base rebars. In my case now I use rebar diameter 8, each 200 millimeters for the top layer in main direction. You can set up a base reinforcement for different layers, and as I have showed you for beams, we have also here some rules, and the best rule here in my eyes to understand is the merge length rule. So that means, if you remember the isolines are definitely not rectangular, they have some fancy shapes, and if we now generate rebars belonging to that isolines, we get for each bar different length, and this is not good for the construction side. So therefore we have a parameter here called merge length, and this parameter check for a difference between two neighbored bars. If the difference is less than, in this case, 25 centimeters, the reinforcement tool decides to define only one bar length and use the longer length for sure. So this parameter can influence your generation rules, and that's quite one of the important parameters. If you insert here a small number, you get different bar length for the slab, and if you have here a higher number, for sure you get less bar marks, because the bars has almost the same length on the supplemental rebar. So in this case I will simply click on OK. Also here I don't like to set up any values again, because I have prepared that already well, very well. And let's check now. Oh, this is the wrong view. Let's go to upwards here. Let's check now for level 1. So you see, this is the supplemental rebar of this results. Okay. you see that we have additional rebar, we have different length, and this is now defined also by this parameter. Now, I'm a bit wondering because normally I don't have such different rebar layouts. Anyway, I do not understand that very well. Let's check again. But anyway, it does not. Let's try to check it again. So anyway, let's check the top rebar and the bottom rebar. Yeah, you see that I have many different bar lengths. But anyway, it's not the case now to discuss that. But you see that first of all, we have all the rebars inserted in the slab. We have different lengths regarding the isolines. We have the base reinforcement, and that's quite nice too. We have additional information if the bar are sitting on top or bottom of the rebar, and using some filter you can hide certain rebars in the bottom representation of rebar and the top representation of rebar. As you can see here, I've already prepared certain views. We can use that filter to hide certain rebars. As you can hear also, we don't see the rebar for the beam because they are also hidden by some filters. And when we switch back to our beam sheet, you see that now the rebar are represented in the sheet of the beam, which in my eyes does not make sense at all. So sometimes I don't like to represent this information in the sheet. So therefore here we use also some filter, but the filter are not active now because we need additional information. And the additional information is the bar assignment, because also these bars are not assigned to a certain sheet. We have to assign all that bar to a sheet. I will use now the sheet of the slab. I will assign the bar to a certain sheet. So that means you have the possibility now to have a value also in the soft sheet parameter. And when we take a look now to the sheet of the beam again, you see that now the elements are not visible anymore because you have some filter. I'm not familiar if you are aware with filter or familiar. So we have some filter where we can switch on and off some rebar elements. In my case, I have switched off the rebar elements for the slab on that sheet. And on the other hand side, if we take a look at this floor plan, we have hidden the rebars of the beam itself. So you have to play a little bit with the filters. So and here we have quite the same concept. We have to represent the rebars not in a realistic way, but in a more or less symbolic way. But what we need first of all is to split the rebar. You see here for the base reinforcement, Revit generation generates a very long rebar. The length of the rebar is around about 35 meters, which is definitely too long to manufacture or to bring on site. So therefore we have tools called split the rebar. And with this tool you have the possibility to select some rebar, and belonging some rules. You can also do some staggering, select which rebar you like to create, what's the maximum length of the rebar, what is the left length of the rebar, and you can, using that tools and dividing some rebar element, as you can see here now, I have divided the rebars in some pieces. You have to do that for sure now for also these elements, but to save the time, I don't like to do that. And the next step is again to do some tagging. And in this case, I don't use the tag all tool because this makes only a tag. I will now use the hide and tag tool. So this is the tool Ausblenden und Beschriften in German. So this tool will check all the elements you select, selecting all the elements, finishing the selection, and then this tool will checking for rebars which has the same layout, hiding the rebars, representing only one bar, as we have seen also on the beam for the stirrups, placing automatically a tag tool and applying that to that sheet. So as you can see here now, you have all the rebar elements. You see here 21 pieces of diameter 10, each 40 millimeters and so on, or 40 centimeters and so on. You see also the additional bars here appearing on the sheet. What we are missing again is the mark, so you can apply the marking as we have seen for the slab, for the beam. You see that also here, same bars gets the same number. So these are the 12-meter bars we have divided. We have at start a 6-meter bar, so therefore this gets a different number, and so on. You can do now this also for the top rebar layer, and afterwards again you can create your bending schedule. You see all the elements here in the bending schedule with the bending information, and same as before, you can print out that bending schedule and, or if you like, bring that also directly on the sheet. So I think I'm quite finished with this representation. So now let's open again for question. So if you have any question, please activate your microphone or please use the chat. Otherwise, I'm quite finished with my part. Okay, it seems that there are no questions. Hopefully you have understood all what I like to tell you. And if there are no questions, I will say thank you for your attention. So now you have first impression of our tools regarding analysis link and all the reinforcement tools. So I think you have all the possibility to install that on your machine, or maybe you have that already done, and to play a little bit with the tools. If you have any questions using the tools, please do not hesitate to contact me. So I think Kaire has all my contact details. You can also contact Georg if you like, especially have some question about all the sales concepts. Otherwise, again, I like to thank you and I say goodbye, and I close the meeting now. And Kaire, I will provide you with the video of this meeting. Hopefully it has worked. And I will maybe give you some Dropbox folder where you can download that. Okay, thank you and bye-bye.